Hello there, thank you for joining me today regarding the final part now of the Marconi microwave radio test set 6200A. This test set originally had a fault on it where the output power RF signal level coming out of the RF output port was too high and you couldn't adjust it, so when you turn the variable control for the RF level, it wasn't increasing and decreasing the level, it was just fixed output. The only time when the output changed is when you turn the level down enough so that the step attenuator, which I've shown you in the previous videos, that relay attenuator will click in and then the output level will drop 10, 20, 30, whatever dBs. So what we've done, we've reassembled the test set now back to how it was. We've got a power sensor connected to port D, which we're going to calibrate in a moment. We've got a spectrum analyzer connected to the output of the RF here, the RF signal output. We have a signal coming in from another signal generator to the counter, so we can check the frequency counter operation as well. And then we'll go into the service mode and then to instrument calibrations mode and show you that, so that you can follow my diagnostics and ultimately to calibration. You won't be able to calibrate your own test set like I can, because there's a secret Marconi passwords which I know to get into that level of menu, which I'll show you shortly. But that the demonstration I'm going to give you, which I'll show you as well, is the diagnostics mode. So at the moment we're generating what is a 0 dBm signal, and we're at 5 gigahertz. It's in source only mode, so it means it's producing a carrier wave output just at 5 gigahertz. It's not sweeping or anything or doing anything fancy, and it's just 0 dBm output. Now we can see when we look at the spectrum analyzer that the level on the spectrum analyzer is not 0 dBm. If you look in the top right, it's actually 10.62ish, varying slightly, dBm, so it's 10 dBs higher than it should be. Now if I turn the SIGGEN output power and I start to turn the rotary control, so as you can see there in that section, this level should change. If we have a look at the spectrum analyzer, while I do that adjustment, you can see that it's not moving, and now I'm at minus 10 dB already, and there's been no movement whatsoever there. So it's only when you step attenuator, you can hear there clicking in, where it jumps, you see. So it's not adjusting the RF level really. It's getting to a certain level and then just jumping with the step attenuator. So we'll set that to 0 dBm again, and it's at 10 dBs higher than it should be. So this means we need to do a calibration. Before we do that, I'm just going to utility menu, you go down to diagnostics, sorry, wrong one, service, then diagnostics, then you go to source diagnostics, and then you go down to where it says here you can do different things with all the test sets, as you can see there on the menu. These are some of the tests that you can do. So we're interested today in doing the source diagnostics, so source control, and then we've got level DAC. Now this is the level which is referenced here, it says level DAC, that controls the pin diode attenuator. Now it's quite a high level at the moment, so if I just do 1000 just for argument's sake, the RF level's not changed on the spectrum analyzer, so if I adjust it to say 500, yeah, it's dropped down already. So it's somewhere between 500 and 1000 where the adjustment is. I think that's going to be too narrow. Again, we were talking in the previous videos about a window for the diode. The more voltage it produces when it's detecting an RF signal, the wider the window will be for adjustments. And when we go into the calibrations menu, which I'm going to show you shortly, it'll want to do that adjustment in 1 dB steps. So if this value here can't change the RF level in 1 dB increments over its frequency range, then it won't be able to calibrate. So that means the diode that I've put in might not be the right kind of diode, but we'll see. So if we have a look at the spectrum analyzer again, and we increase the DAC level, I think it was around about 800, I think, when I saw it adjust last time. There we are. So that's, I can make a very fine adjustment. So that level there is plus 10 dB dBm, and that level is 832. That's 831, and we can adjust it very finely, but we can't adjust it in 1 dB steps, and that's within 5 DAC values. So basically what that means is this level here is too fine, but what I will say is that's a vast improvement on before, because prior there was no adjustment whatsoever. There was either all RF or no RF, and there was no in between. So that is, in my mind anyway, not going to calibrate, but we'll see. And I think it could be a bit of a failure, this repair. I might have to obviously buy the original part, but it just shows you that we're nearly there. The diode is giving an output voltage, the ALC is picking it up and it's trying to control it, and the RF level's going up and down, but the RF level's going up and down too coarsely. It's not fine, and it should be fine. So as we can see there, if I adjust it again down, so that's just literally within 1 increment. You can do, it's not actually a 1 dB step, is it? It's jumping more than 1 dB, is that by far, but there is some adjustment there. Well, that wasn't there before. It was either there or there, sort of thing, and there was no middle ground. So we're nearly there. If we just get the right diode to go in it, then I think we'll be able to do it. Okay, so the next phase is to check the instrument calibration. Now we can do a calibration mode. So before we do that, I'll just do a preset. We'll go back to default settings. We'll go to readout for frequency, because I just want to check the frequency counter works. We'll go to measure counter, and at the moment I'm injecting here on this port 5.29 gigahertz, which it's correctly reading there. If we look at the signal generator, that's 5.29 gigahertz at minus 30 dBm, so it's quite sensitive. If I put the doubler on, so we've got to 18 gigahertz, sorry, 10 gigahertz, we're on 10.59 gigahertz on the SIGGEN, and we're getting 10.591 gigahertz there. So that's obviously working. Right, so we know the frequency counter input's working. So what we need to do now is we need to remove this. We'll just go to source. We will go to yes, we're okay, calibration, and then there is sensor cal. Now this is where we take the power sensor. This power sensor is connected to the D input, and this calibrations data here that's on this label is entered in to the test set, and the calibration data is all held in this, which I've already manually entered. So we connect the detector first of all to the power reference port, because we need to calibrate the detector first before we do any calibrations of the RF output. So we'll connect that up. It's more difficult than it looks when you've only got one hand available, but that's life. And of course it never wants to go on when you're filming, it's a pain in the backside. All these microwave radio things are all you know, mechanically faffing about. Wave guides, SMA connectors, N-types, the sort of high precision N-type plugs. They're not the standard kind of N-type plugs that you get on most equipment. They're a nightmare sometimes to deal with because they've got very tight mechanical tolerances, and sometimes you'll be turning them forever and ever and ever and they'll not be biting, and then suddenly they get the thread and they go on. And that's the thing with microwave stuff, you'll come across this a lot. It's a constant routine of calibration, faffing about mechanical stress and parts, because obviously when you're attaching things like SMA and N-type connectors, if they're not tight, then as you'll see in some of the other videos that I'll do, when we're looking at impedances in a Smith chart, S parameters, things like that, just having them not tightened to the correct torques makes all the difference in a measurement, and you'd be amazed at that, and I'll prove that and show that in a video, one of my next videos. So we connected it to the calibration port. This gives 50 megs out at 0 dBm, and that's a reference that this sensor's calibrated against. So we're using the calibration table that's already held within the memory, which represents this sensor, all the linearity data, and now we're going to do continue, and now it's going to zero the sensor, and then what it will do, it will put 50 megs on at 0 dBm as the next step, and it will then calibrate the instrument against the detector. And that means then that when we've done that, we can move the detector from the reference port to the signal output, and we can go into the instrument calibrations menu and see whether it can self-calibrate. And how it self-calibrates is it simply puts out the microcontroller, chooses a frequency between 10 megs to 20 gigahertz, depending on whether we do broadband or narrowband power calibration, puts out a predetermined RF level that it thinks it should have, for example 0 dBm at say 1 gigahertz, and it's looking to see if this detector then, when connected to that port, can see 0 dBm at 1 gigahertz, and then it will adjust the RF levels at half a dB or 1 dB increments up and down through the dynamic range of the test set, and likewise across the entire frequency spectrum of the test set. So it can take some time to do that calibration, but that's basically what we've just done. We've calibrated it, we're still on the frequency counter, we're ready to connect to this port now, so we'll connect to this signal port, and again a lot of faffing about with the precision. These are precision ends, these N-types, and they're very difficult sometimes. So we'll preset the test set, and we'll just go back to default settings. Right, okay, so we'll go